Okay, so good morning. Welcome back. We were discussing negative feedback and we came up with the architecture of differential amplifier, which evolved kind of naturally. And before going there, we were delving into this architecture, this classical feedback architecture that you are familiar with. And we drew the parallel and we came up with this. This is some R out of your differential amplifier. And we understood that this GM is PE. This is equivalent to a differential amplifier realized in the following fashion. Okay, so what is the most from your knowledge of E250? If you have to analyze the negative feedback loop, what is the most critical thing that you are looking for? First thing that you are looking for? If you have to analyze a negative feedback loop, right? Let's assume the top left figure, this one. If you have to analyze a negative feedback loop for its gain, stability, and so on, what is the thing that you look for? Loop gain, right? Open loop gain, right? So in this case, it's GH, right? Two blocks, pretty simple. You look at it, multiply G times H, and then do all your analysis, right? So, but experimentally, you have to figure out what is the loop gain. What will you do? Yes. Let's say you are in the lab, you have this loop, you have access to all the terminals of the loop, let's say, and you want to find out the loop gain. What will you do? Yeah, in order to get frequency response, you have to do something, right? You have to find the loop gain first. How will you find the loop gain? You have to break the loop. You have to first break the loop because if it's in the closed loop, if the loop is operating properly in the closed loop form, then V0 is basically independent of the loop gain almost, isn't it? So in order to figure out what is the loop gain, you have to break the loop somewhere. So in the loop, in this block diagram, you can break it anywhere. It doesn't matter. You can break it here. Let me break it here. Let's say you break it here and you apply a test voltage V test and see what comes back, right? So this becomes G times V test. This becomes G times H times V test. This becomes minus GH times V test. So the ratio between whatever comes back, let me call this V return. So ratio of whatever comes back to whatever you applied, negative sign of that is the loop gain, right? So your loop gain is minus V return by V test. If all the variables are in voltage domain, and that's what you are interested in, right? So you can just apply a test voltage and see whatever comes back. Now, in principle, in the loop, you can break it anywhere, right? I can break it here as well. Doesn't matter, I can break it here, apply the voltage here and observe the voltage here. I'll get the same thing. So you'll get minus G of H, minus GH. Whatever comes back, right? I broke it. Let's say you apply a voltage here and you figure out what comes back here after breaking the loop. that will be G minus of G times H, right? That's the V return. So, so one of the reasons this works in this block diagram, is because there is no loading effect. Because if you break the loop, you are essentially saying that I am removing whatever was connected to that loop, but it doesn't change the characteristics of whatever it was driving. Right? So in this case, let's say H was the input impedance of G, let's say, is infinite, then H doesn't load G, G doesn't load H. Okay, or the summer doesn't load the H. So if I break the loop, if I break the loop in the position that I have shown, then breaking the action of breaking the loop doesn't really change the characteristics of either G or H. That's what independent of loading means, right? But in the circuit on the right, that's not particularly the case, because if let's say I break the loop here and apply a TS voltage here, and I observe the voltage at this node, right? So do you think the characteristics of this block will change? In the sense that, let me call this Vx. The relationship between VE and Vx, is it independent of this feedback factor or dependent on that? It's dependent. It's dependent because GM was getting loaded with this stack of resistances. Now, if you remove the stack of resistances, right, the gain in the presence of the resistances would have been GM times R out parallel combination of KR. Correct. The relationship between Vx and Ve. So, okay, let's not start from here. Let me start from here, right? So, let me take 2 steps back, right? So, let's say I break it here. Why is the eraser not working today? So, let's say I break it here. Oh, by the way, another important thing is that when you are finding out loop gain, you have to desensitize the input, which I forgot to say. Okay? So loop gain is not dependent on the input, so you have to desensitize the input. That's an important thing. So you desensitize the input here incrementally, and you apply a V test here, and you try to find out what is V return. So V return. What is V return in this case? This should be pretty simple, right? What will be V return? Now tell me. If you apply a V test, what is the current from this GM? GM is a voltage controlled current source, right? It's a VCCS or a transconductance, or you can think of it as a short circuit current gain in whichever terminology you are comfortable with. If you apply V test in the direction I have shown, what will be this current? GM V test, but I mean, you have applied the V test at the negative terminal, so it will be minus GM V test, right? So it's minus GM V test. So minus GM V test flows into a parallel combination of R out and KR, right? So V return will be minus GM V test times R out parallel KR. So what will be a loop gain? Loop gain is minus V return over V test, which is which is GM times R out parallel, yeah. Okay. But if I now decide to break the loop, if I decide to break the loop here, and let's say this R out is the intrinsic part of the GM. So let's say I decide to break the loop here and do the same experiment, and I apply V test here, and I will observe V return here. Okay, I made a mistake here. So this V return should have been scaled down by a factor of K, right? So the voltage that I see here is this. This should have been divided by K, right? So by K. So if I apply a V test here, this V return will be what? This voltage becomes V test by K. So this current becomes GM times V test by K, negative direction. So this V return voltage becomes minus GM times V test by K times R out, right? So your loop gain G of H becomes minus GM by K times R out, right? So this loop gain expression and this loop gain expression are not identical. And the reason it's not identical is because in the second case, we haven't taken into account the effect of loading of GM. Because the moment I disconnected this, right, I took away the loading of KR on GM. Okay, so that's why this becomes different. So in this course, what we will do, we'll try to find out a place of breaking the loop where it's convenient to break. By convenient to break, I mean you should break the loop in a position in such a location where the effect of breaking the loop doesn't affect the loading, right? So which means that the input of the error amplifier, if you break, then no loading condition gets changed. So it's best to, it is most convenient to break the loop at the input of the error amplifier. Okay, so which means what I'm saying is break the loop. Try to break the loop here, or at this point, if it's possible. Yeah, so you have, okay, so in other words, you have to break the loop at a position where there is no current going in. There is no input current going in. For example, at the input of the error amplifier, the input current is 0. Since the input current is 0, since it's an infinite impedance load, input current is 0. Since the input current is 0, it doesn't matter if you break at the input, the previous part of the network, which was driving that node, doesn't get loaded, right? So find a position in the loop where the input current is 0 and break it there. Okay, good point. So we don't have bandwidth to go there. So his point is, if there is a circuit where you cannot avoid this. For example, if there is a circuit where there is no such position where you can effectively break it without avoiding loading, then what do? You can do that also, but in that case, you have to put back that loading effect. In this case, we can put back this loading effect. Even if I break it here, right? Even if I break it here, I can put back that loading effect by making this KR here. Right? So that restores the effect of loading, but we'll not get there in this lecture, in this class. We'll assume that you have a position where you can break reliably, and will always break at the input of the error amplifier. Okay. Oh, yes.
What is the loading effect in this? We expand this differential amplifier.
Right. No, you don't even have to expand the differential amplifier, right? The symbol, what is the input of the symbol? So let me call this V1, this is V2. So this becomes V1, this becomes V2, right? So looking into V1 or looking into V2, you have infinite impedance, right? So that's what you are saying. So looking into V2, you have infinite impedance, right? So V2 doesn't, the input of your GM doesn't load the node that it's following, right? It doesn't load this node. You don't have any current flowing in, so you can reliably break it. Okay.
It's already breaking.
Yeah, it's not broken. The signal is flowing, but not in the terms of currents. The signal is flowing in terms of sensing a voltage, right? If the signal flows in the form of drawing some current, then you have a problem. Then you have to take into account loading effect and insert the loading back in some way, right?
What was the point of where were you previously breaking?
Previously, I was breaking here. Previously, I was breaking here. Previously, I was breaking here because you were not anywhere not drawing any current. So by breaking the loop there, you didn't do any change as far as drawing of current is concerned, right? If you don't draw any current, there is no loading. Okay.
Problematic case where we are breaking, what was that?
Okay. So in this case, here the problematic case was this stack of resistances was drawing current, right? So now if you break, so you are disturbing the quiescent, or you are disturbing the operation of the circuit, because it was supposed to load current under natural conditions, which it's not, because you took away the loader, right? So if you have to restore, then you'll have to put back it at the other side of the circuit, other side of the of your breakpoint, right? But I mean, so this is in principle, this is pretty simple to do, but it requires a bit more of analysis. So we'll not go there. No, it was a demonstration to show that, I mean, if you have to draw an analogy between this GH plot, right? This GH plot gives you an impression that you can, GH block diagram gives you an impression that you can break the loop anywhere without, for finding loop gain, and it should be fine. But in a more practical scenario, this GH block diagram essentially assumes that H and G are independent of each other. In reality, it loads, right? They are not particularly independent. In fact, in practical circuits, you will see that if you take more circuit design courses, you will see that neither G nor H are independent of each other. So you always load. So you have to, if it loads, then you have to put back the loading in some way and then figure out. And this is also a single loop. In practical circuits, no loop, no circuit is a single loop circuit. So you'll have multi loops, then you have to figure out ways of analyzing multi loop systems. Okay, fine. So this is as far as finding GH is concerned. Once you find GH, then you find steady state error. And when we go to frequency response, you can find frequency response and so on, right? So that's not the part of the next part of this discussion. The part of the next part of the discussion is to make this differential amplifier a better differential amplifier. And assuming both these are amplifiers, both these transistors are identical, the gain was how much? So when we said this is GM, this is R out, plus minus. So GM was GM by 2, where GM was the GM of these effective individual GM of these transistors, M1 and M2, and R out was RD parallel to RDS. Now, this is similar to our case of common source amplifier. Right? This expression is similar to the case of common source amplifier. With a flip of sign, of course. Now, the question is, not before going to the question, the problem, we have encountered this problem multiple times, that if we have to, if we use this resistance RD and we want larger and larger gain, we have to increase VDD, right? We did multiple problem sets on this. We figured out what is the value of VDD or what is the value of RD that is required to achieve certain gain and so on. And the conclusion was, if you have to keep on increasing the gain, you have to keep on increasing RD. If you keep on increasing RD, the quiescent drop across RD becomes too much, and which means the transistor goes into linear. And in that, to avoid that, we have to raise VDD. And this seemed to be the only solution. So put in another way, the gain of this stage was limited by the quiescent drop across RD. Right? If you have to increase the gain, there was no other way but to deal with that quiescent drop across RD. Okay. So now the question is, can we get rid of that? This is something that's probably not acceptable. because if you increase VDD, you are increasing power consumption. For the same current, you are getting higher, you are drawing the same current from a higher power supply, which means your power consumption is bad. That is not something that is desirable. So is there a way of mitigating that, right? So in fact, there is, and the way we think about it is the following. So what is the impedance looking down at this node? Let's say neglect RDS. What is the impedance looking down? Infinity, right? What is the impedance looking up? It's RD. So now why is the impedance looking down infinity? It's because I'm looking into the drain of a transistor, bias in saturation, right? So the question is it possible to have a drain of a transistor looking up also? Can I have a transistor? Can I connect a transistor in such a way that looking up also I find a drain? If I can find a transistor, looking up is also a drain, then the problem looks to be solved, right? Then I can get really high gain. And which means, and also I don't have to get infinite supply voltage to get the gain, because it's a parasitic art, right? It's an incremental resistance I'm looking for. I'm not looking for an exact resistance. Because, okay, so the incremental current will still be GM times VI. This GM times VI, if it flows into a very large resistance, I get a lot of gain, right? So now the GM times VI is flowing into a parallel combination of RD and infinity, right? So I'm getting GM times VI times RD. If RD is also pretty high, right, then I can get. And how do I get high RD? We have to look into a drain of a transistor, okay? But we already, I saw some head scratching because, I mean, how do I put a transistor there, right? Whose drain is looking, drain is at the bottom side, because drain is supposed to be at the higher voltage, right? So essentially what I'm saying is that, can I do this? A transistor terminals are not decided, right? Transistor is I mean, geometrically or physically, it's a symmetric device. You can flip the decision on whether one terminal is drain or source depends upon which side is of higher voltage, twice and twice, right? So if I do this, for example, can I say that if this is VDD, let's say this is biased, will be something. This is also biased, and top of that I have applied an input. This is GMVI. But what is, so is this terminal drain or source? Source. And how do you know that? Geometrically or physically, there is no difference between which terminal is source and ground. It's a symmetric device. So how do you know that which terminal is source, which is ground, or which is drain? Arrow, you decide the arrow, right? In present, I mean, actually, your device is like this, right? So how do you decide this is source, this is drain, or this is drain, this is source? Yeah, no, current comes from a higher voltage. So essentially, the side that is pinched off is the drain, right? And the pinched off part is the higher voltage part, right? So if I apply higher voltage here, right? If this is VDD, for example, this is ground, I'll have the charge distribution like this. If this is VDD, this is ground, the charge distribution will become like this, right? So that's how your drain and source terminal can get flipped. But in this case, clearly, it's not flipping, because current is flowing from top to bottom, because I have higher voltage on one side, which means this naturally is a drain and this is the source. So then once you decide which is source and drain, you can decide to place the arrow. So arrow is a consequence of this, right? It's not a BJT where you know it a priori. Okay, so naturally this is a problem, because now looking up impedance is definitely not infinity, it's 1/GM, right? So then the question is, can we do this? And as it turns out, we can do this, but not with the NMOS transistor. So herein comes the next part, and the next part is the following. No, it is source. That's why it's 1/GM. right? So the quiescent conditions decides whether it's source or drain. So from the quiescent analysis, you see that which side is higher voltage, which terminal is of higher voltage. In this case, clearly the upper terminal is of higher voltage, so that becomes a drain. The lower terminal becomes source. If it's source, then looking up impedance is 1 over G. Okay. So now the correct. Right. Yes. You can make it to be a large value, but then your gain, I mean, so what is the gain now? So let's say this is M2, this is M1, this is GM2, this is GM1. So your gain is what? GM1 times, so if this becomes V0. V0 becomes minus GM1 VI times 1 over GM2. Right? So your gain becomes minus GM1 by GM2. So GM1 and GM2 are of the same order, right? You cannot make it too different because ultimately same current is flowing through the stack. You can probably make the W by L to be slightly different, but how much will you make before it goes out of, before it goes into subthreshold? So essentially, I mean, the problem is you get back to the same problem that you cannot get too much gain. And the root of the problem is that you are not able to manufacture a transistor which in which case the lower side of the terminal is a drain. Okay, the lower side of the terminal in MOSFET is a source, and you want, in order to fix this problem, you would want a lower side of the lower voltage terminal to be drained. Okay, so if we can get a device which behaves exactly like in MOSFET, but just that the direction of source and drain are flipped, then the problem is solved. Okay, so as it turns out, there is a device, it's called PMOSFET, right? It's a complementary to that of N. So let me sketch the device, you'll understand readily. So this is your N MOSFET, let's say, this is P-type body. Yeah. So it's your drain, and this is gate. Let me call this drain and source. When I call this drain and source, I assume that the side I am calling drain is at higher voltage. Okay. And if you are in inversion, right, which means VGS is at VGS is greater than threshold voltage, you have mobile electrons underneath the channel. Okay. And the carriers flow from left to right, electrons flow from left to right. So the current flows from right to left. Okay, that decides which is drain, which is source. Now, as it turns out, there is another type of device which has everything same, but the dopings are different. Like wherever you have P, you have N. We call it again, we call this source, this is drain. And in this case, assume that the source is at higher voltage than gate. Okay. Assume that the source is at higher voltage than gate. So effectively so let me do the analogy side by side, then it will become more clear. So the electric field in the NMOS side goes from gate to the body, gate to the channel, because the gate is at a higher voltage than source. So in this case, in the circuit, in the diagram on the right, the source is at higher voltage than gate. So the electric field will go from bottom to top, right? So it will go like this. This is E. So in the NMOS, this is NMOS, PMOS. In case of NMOS, you attract negative charges under the channel. In case of PMOS, what do? You attract positive charges under the channel, right? and positive mobile charges are holes. So you get holes underneath. Okay. So in case of NMOS, the pinch off was happening at the site where you had higher voltage, right? In case of NMOS, sorry, I confused myself. So in case of NMOS, the pinch off was happening at that junction where you had higher drain voltage, right? In case of NMOS, in case of PMOS, what will happen? The same thing will happen, right? But ultimately, what happens? The pinch off happens where the electric field almost pushes to zero, right? Or not zero exactly, but around threshold voltage. So same thing will happen in this case, in case of PMOS, and your pinch off will happen here. Okay, but the critical thing is that the supply, the current, the holes move from left to right, right? The holes move from left to right, but the current is also from left to right because holes don't have negative charge. Okay. So what implication does this have? The implication that it has is the following. So if I go to the symbolic representation of NMOS, and the symbolic representation of PMOS is just the reverse, just that I have the arrow on the source terminal. And the direction of arrow points to the direction of the current flow, right? So in this case, the current was from top to bottom. In case of PMOS, the current is from source to drain, right? Okay. In case of an NMOS, in order to turn the transistor on, you had to apply a positive voltage between the gate and the source, right? If you had this voltage should have been VGS should have been greater than threshold voltage, right? Or in other words, it had to apply a VGS which was threshold voltage plus some overdrive, some additional voltage in order to ensure that there were charges in the channel. In case of a PMOS, the gate voltage should be lower or higher than the source. It should be lower than the source because you are trying to attract holes in the channel, right? So everything is flipped. So this should be VSG should be some threshold voltage plus overdrive. Okay. So naturally, I mean, since both these devices, as far as the circuit design is concerned, behave identically. So naturally, all the equations that are valid for NMOS will also be valid for PMOS. Okay, just that the directions will be flipped. So the equation for an NMOS for current in saturation is IDS is equal to half okay. So in case of a PMOS, it will not be IDS, it will be ISD. It will be so it will be a different color. So in this case, it will be ISD is equal to half mu P Cox because P subscript is denoting the mobility of the holes. So mu P Cox W over L times. Now help me out. What will I write? VSG minus threshold voltage whole square times 1 plus this is lambda P VSD. Okay, so this was lambda N ideally. Now, in truest sense, what do you think the threshold, the sign of threshold voltage is? Which is, I mean, in case of, okay, so if you look into the literature, you will see that this threshold voltage of a PMOS is negative, because with respect to NMOS, you have to apply a negative voltage. Right? In case of an NMOS, you have to apply a positive VGS in order to turn it on. In this case, you have to apply a negative VGS or positive VSG. So sometimes you will see that threshold voltage is mentioned as minus of something, but we will essentially ignore that, and we will say that we are always bothered about the mod of the threshold voltage because we are interested in using it in this form. We don't want to get into those negative positive business. So if you find somewhere the threshold voltage is of a PMOS is minus something, you assume that is because of this flipping thing, and you take mod of that and go ahead. So in this course, we'll always use positive. Even if I mention negative, I'll say that mod of this is positive, and then so that we are not confused about it. Okay, so I just, in order to distinguish between NMOS and PMOS, the threshold voltage of NMOS will write as VTN, and threshold voltage of PMOS will write as VTP, right? Okay. So in order to turn the transistor on, you'll have to apply a VGS of greater than VTN plus some V overdrive. The same thing in this case, you'll have to apply a VSG should be greater than some VTP plus V overdrive. Okay. So what is the condition of saturation in case of NMOS? The drain voltage has to be greater than gate minus threshold voltage. What do you think will the condition in the PMOS be? So it might be useful if you think it in this way, that in case of a NMOS, there is a minimum value of drain voltage, right? Before it goes out of saturation. You can lower the drain voltage to a certain extent. Correct? In case of a PMOS, what do you think it will be? It will be lowering of drain or increase of drain? So increase of drain. So there will be a maxima for the drain, right? So in case of this, there is a minima of this minima of VD determines the edge of saturation. So in this case, the maxima of VD will determine the edge. And what will that maxima be? So in this case, your VD should be then less than equal to what? Hold on, you had a question. Yes. I didn't understand which one. Ah, okay, sorry. Yeah, you're right. Yeah. So I had run ahead of myself. Yeah, thank you. Okay. So what do you think will this condition be? So in this condition, in case of an NMOS, the drain could have gotten one threshold voltage lower than gate, right? So in this case, drain can get one threshold voltage above the gate. Correct? So VD has to be less than VG plus VTP. Okay. So these are twice and twice, these are the only differences, right? So you have to just keep track whether it's an NMOS or a PMOS. You're comfortable with NMOS, that drain has to be one threshold voltage lower at max. In this case, the drain has to be one threshold, can go up to one threshold voltage higher than gate while keeping the transistor in saturation. Yes. Yeah. So we'll have absolute value always, right? So when you do device courses, you will take TP to be negative, but for all circuit courses, I assume it will be positive. Ideally, it should be mod of VTP, but yeah, we don't want to get into those symbolic complexities now. Okay, fine. So this is as far as the quiescent picture is concerned. So everything in case of quiescent picture is magnitude-wise identical, but direction-wise flipped. So similarly, in the incremental picture, everything will be same as far as the model is concerned, but the directions will flip. Okay, so the direction in case of your NMOS was this is GM times VGS RDS. In case of a PMOS, I still have a gate. The source is on top, right? Because if I have to draw an analogy, in this case, the source will be on top, which the current is flowing from source to drain. This will be GMP, we call it GMN, this will be GMP times phi, GS or SG? SG, right? And this will be RSD. Okay, so now firstly, this RSD and RDS are same, right? Because as far as the resistor is concerned, it really doesn't matter what is the direction, right? So it's better to always not complicate that and represent it as RDS. And this becomes the drain. Now, there is another popular way of this is correct. You can do all your analysis using this, but the more preferred way is the other is the one where you flip the direction of the current source and looking up, because ultimately we don't want to learn to analyze a new device. It's essentially the same device incrementally. We are comfortable with GM times VGS, right? So we'll just say that we'll model it as GMP times VGS, just as the reverse, the current direction will flip. And this becomes drain, this becomes source. This remains RDS. Okay, fine. Any questions? Pardon? No. I didn't do any change, right? I just changed this VSG and make it VGS. So I had to change the direction also. Right? So this is what? This is equal to minus GMP times VGS. Right? So now if I have to remove that negative term, I have to flip the direction of the current. So I did double negative. So now incrementally, if I have to realize a common source amplifier using a PMOSFET, right? What will you do? Let's assume this is your model of your PMOS, right? Not assume this is your model of your PMOSFET. So you have to design a common source amplifier. So what did you do? Talk me through the steps of how will you do it with the NMOS transistor, and we'll do the same thing with case of PMOS. Where do you apply the input? You have an input, VI, RS. Where will you apply the input? At the gate. In a common source amplifier, apply at the, in this case, a single transistor common source amplifier, apply at the gate, right? So we will apply it at the gate. Fine. So the direction of, so if I apply at the gate, what do you do at the source? Source should be incrementally grounded, right? In case of a common source amplifier in the NMOS, the source was incrementally grounded. So we grounded the source incrementally. Where will you connect the resistance R? At the drain, right? So at the drain R. And where will you take the output? At the drain, right? So this becomes V0. So what will be V0 over Vi? Right, so source is grounded, right? So S goes, Vg is equal to Vi. So the current, this current is GMP times Vi, but this current you are drawing up, right, into the ground. So effectively the current that you are drawing from this node is minus GMP times Vi, and you are drawing it out of a parallel combination of RL and RDS. So this becomes RL parallel RDS. So expression wise, it's identical. Okay, expression wise is identical, but if you have to do, if you have to also do a biasing of this, right? This is the incremental picture. So what will be the bias picture? In case of an NMOS transistor, the bias picture was this. Let me write it in this form, VGS of certain value. In case of a PMOS, it will be the current goes from source to ground. Your resistance is connected to the drain. This is source. You apply a voltage here. Source has to be incrementally grounded, but in quiescent wise, what does it need to be in order to ensure that the quiescent current flows from top to bottom? So this is source, this is drain. In this case, in the case of PMOS, the source is on top. It has to be incrementally grounded. So it has to be at what, zero potential or some non-zero potential? Some higher potential, right? Some higher potential which doesn't change. That's what incremental, incremental short means it's a constant potential. Constant is also a zero. In case of an NMOS, the zero would have been fine because the source is supposed to be at lower voltage. In case of a PMOS, the zero wouldn't just cut it, right? You have to go to a higher voltage. And the highest voltage that you can find on the chip is VDD. So connect to VDD, right? And gate, again, you bias and apply an input. Some bias, VB, which has to be at least one threshold voltage lower than VDD, right? So VDD minus some threshold voltage plus overdrive lower. And you take the output from here. Okay. Okay, we'll stop here. We'll meet in the afternoon anyways. BS is grounded in this case, right? I didn't understand. Why should VS be smaller? I mean, under quiescent condition, VS has to be higher, right? Otherwise, why will the current flow from top to bottom? Okay, fine.